Good day, everyone. My name is Lalaise Lim W. Gas, and I am here to report to you the topics from translations to Theorem 25. To start with, let us describe the products of two translations. Let us take M and N be lines parallel to each other, and let us pick point P, an arbitrary point of M, and Q be the foot of the perpendicular line of M and N. Then if N is a unit normal vector to M and also to N because they are parallel, we get the product of M and N of X is equal to the omega of Mx minus 2 times the distance of omega of Nx minus P n of times N, and that is equal to X minus 2 times the distance of X and Q, n times n minus 2 times the distance of X on P, n times n plus X minus Q, n times n of n times n. Then X plus 2 times the distance of P and Q, n times n. That would be equal to X plus 2 times P minus Q. The last step uses the fact that the line PQ is perpendicular to M, and since M and N are parallel, then the perpendicular line PQ is also perpendicular to M. So by definition, that's the definition, let L be any line and let M and N be perpendicular to L. The transformation of omega M and omega N is called a translation along L if the lines M and N are not equal. The translation is said to be non-trivial. Theorem 23. Let T be a translation along L. If L prime is parallel to L, then T is also a translation along L prime. Theorem 24. Let T be a non-trivial translation along L. Then L has a direction vector v such that T of x is equal to x plus the direction vector v for all x element in E squared. Conversely, if v is any non-zero vector and L is a line with direction vector v, then the transformation T determined by T of x is equal to x plus v is a translation along L. Okay, the proof for Theorem 24. Let n be a unit direction vector for line L. Let P be an arbitrary point of E squared. Let alpha and beta be lines perpendicular to line L, as you can see in our figure on the right side. Let A and B be the unique numbers such that P plus 8 times n is an element of the line alpha, and P plus Bn is an element of the line beta. Our formula becomes product of alpha and beta x is equal to x plus 2 times P plus An minus P minus Bn. So simplifying, that would be x plus 2 times A minus B times N. If T is not equal to 1, we must have A is not equal to B, so that 2 times A minus B times N is the required direction vector. Conversely, suppose that for each real number lambda, we define a mapping of translation of lambda by T of lambda x is equal to x plus lambda times n. If A and B are any two numbers such that lambda is equal to 2 times A minus B, we construct alpha is equal to P plus A times N plus N perpendicular, and beta is equal to P plus Bn plus N perpendicular, and observe that T lambda is equal to the product of product of alpha and beta. Okay, now let us define a term. No? The set of all lines perpendicular to given line L and E squared is called the pencil of parallels. The line L is a common perpendicular for the pencil. We note that taking any line M in E squared together with all lines parallel to M would be an equivalent construction. So far, we have discovered that the product of two reflections in lines of a pencil of parallels is a translation along the common perpendicular line L. We now investigate further the algebraic structure of the set of isometries formed by reflections of such a family. We begin with translations. We denote that set of all translations along L by trans of L. So as you can see in the figure on the right, figure 1.24, a pencil of parallels with common perpendicular line L. Theorem 25 is the translation along L is an abelian group isomorphic to the additive group of real numbers. Similarly, the translation of mu and lambda of x is equal to t sub lambda plus mu of x, because lambda plus mu is equal to mu plus lambda. Translation along L commute, so it has the commutative property. Further, setting lambda is equal to 0 yields till 0 is equal to 1, and translation of lambda and negative lambda is equal to t sub 0 is equal to 1, so that the inverse of t of lambda is equal to t negative lambda. Thus, the translation along L is a subgroup of E squared. Furthermore, the mapping from lambda to t sub lambda of R to translation L is an isomorphism. This is seen by observing that t sub 0 is equal to 1 and t sub lambda raised to the power of negative 1 is equal to t sub negative lambda, and t sub lambda times t sub mu is equal to t sub lambda plus u. Let P be the pencil of all lines that are perpendicular to a line L. We denote by reflection of P the group generated by all reflection of form omega M, where M is an element of P. In other words, reflections on P is the smallest subgroup of J E squared containing all such omega M. In turn, translation of L is a subgroup of reflection on P. In order to discuss the algebra of reflection of P, we need to be able to compute the product of any number of reflections in the family determined by P. We already know that in our notation, the product of alpha and beta is equal to T sub lambda. We now take three lines, alpha, beta, and gamma of P corresponding to the numbers A, B, and C. Then we have the product of the three lines, alpha, beta, and gamma is equal to omega of alpha, the translation of omega alpha and T sub 2 times B minus C. That will be equal to the omega alpha times x plus 2 times b minus c times n. Then that would be omega of alpha times x plus un, where mu is equal to 2 times b minus c from the theorem earlier. X plus un minus 2 times x plus un minus p minus n times n. Then x minus 2 times the distance of x minus p n times n plus 2 a plus mu times n. Then x minus 2 times x minus p n times n plus 2 times a plus minus b plus c times n. X minus 2 times x minus p plus a minus b plus c n type of n times n. We recognize the right side as the formula for reflection in the line's element P, passing through the point P plus D times N, where D is equal to A minus B plus C. Thus, the product of three reflections in lines of P is a fourth reflection in a line of the same pencil P. This is our first instance of a three reflections theorem, which plays such as an important role in classifying the isometries of plane geometries. So